I'm just going to say this QR code is a link to the GitHub repo with all the slides and the source code. So if you want to take a snapshot of that now while I'm talking, that way you know you have a copy of the slides and you don't have to pay attention anymore. So as I was nicely introduced, I've been working in the industry for about 20 years, over 20 years now. I said 20 years and now it's well over 20 years. I started in 1999 with Sun Microsystems when Y2K was a thing. And I've been coding in Python for about over 20 years. And I've also been, I kicked the tires of AWS back when it was just S3, EC2, and SQS. So I've been using kind of both for quite a long time. And these days I'm a senior cloud architect, whatever that means, at Fourth Theorem. Just a quick shout out to Fourth Theorem. We're a technology consultancy focused on AWS and serverless. We sort of started off agnostic, but everyone wants AWS, so we're AWS. We help with kind of cloud architecture, application modernization, and high-performance computing. I'm giving Fourth Theorem a shout-out, apart from the fact they're my employer, but also because as one of the clients, Renaissance Re, that the problem that I'm going to be talking about came up. So, it seems fair to give them a shout-out. So what this is about is it's about solving a problem. I want to kind of give a go through kind of, seeing a problem in the real world, and then the kind of process I went through to solve it, to figure it out and to solve it, and the tools and the different approaches I took along the way. There's always more than one way to do a thing, so this isn't the right way to do it. This is just sort of the way I picked because the tools I had to hand, and so that's the way I went. I'll be talking a little bit about AWS, specifically S3, a bit about HTTP and TLS, just because I touch on that, so I have to talk about them. I'll talk about boto3, which is the Python SDK for AWS, Python, funny enough. And a bit about a tool called mitmproxy, which I'll explain what it does in a minute. I'll hopefully be talking just enough about each one to give you a flavor of what I'm talking about so you can understand what I'm talking about, but I don't want to go too much in depth or else I'll be here for like 2 hours. So before I can talk about the problem, I have to tell you about the setup, like what is the system we're talking about here and how do they fit together. I had a very complicated big diagram and I had lots of explanations and I decided, you know what, the bit that you care about is there's a large-scale high-performance computing computation spread out over thousands of containers running in Fargate or in Lambda in AWS. These all essentially do their computation in the container, but they'll read and write a lot from S3. We put all the data into S3, and there's gigabytes read and written from these containers and thousands of requests potentially from each one. So the bit we care about here is lots and lots of containers, talking to S3, doing lots of heavy lifting. If you do want to know more, there's actually an AWS blog post on this, so if you want to go to that, where we actually talk about much more depth about the system, and if you're interested in building high-performance computing stuff in serverless, this is a pointer and the way to go. So we have all these containers, we have them talking to S3, and so everything was working great, doing lots of things. But the problem is we got one of the most dreaded questions. When you're operating a large-scale system and you have monitoring, you have dashboards, you have all sorts of things, you think you're covered, and then someone comes up to you and goes, why is my stuff so slow? And you go, I don't know. And that's never a great place to be. And we did the usual thing. We started checking the logs, we started checking kind of metrics, alarms, everything. We just couldn't see any reason why sometimes when running these computations, it would just take a long time. And we were stuck like this for a few days. We were trying to figure our way through the code and through the process to figure out what's going on. And luckily, we eventually started seeing some errors in the logs. These would be very infrequent, but we would see, the important bit here is you'd see the too many requests. And this started giving us a hint as to what might be going on here. We kind of started making guesses here. But we said, okay, we're seeing this occasionally. Does that mean that we're triggering a lot of S3 request retries? So when we're talking to S3, are we just somehow triggering a lot of retries? And what do I mean by retry? Like, and rate limits, like what does that mean in this context? And like, isn't the cloud infinite? Unfortunately not. S3, for example, even though it has huge capacity and can take a lot of traffic, does have a default rate limit example for example, of 3,500 requests per second when you're writing objects to it. So there is actually limits. AWS puts limits on things for sensible reasons, usually limitations of the system, limitations of the economic model. They might make a profit if they didn't actually put some limits on some things, so they have to work that out too. So S3 in this case has a limit. And so when you hit this limit, you might get a rate HTTP 429, which is like a rate limit exceeded error. So we were starting to work on this theory that all these jobs reading writing from S3 might be triggering this a lot. But the thing is, we're only seeing the error very occasionally. So on the face of it, you go, well, if it's only hitting it once or twice, maybe it's not happening that often. Now, the thing is, boto3 does some stuff under the hood when it's talking to S3. So here's some code where we basically import boto3, get the S3 client, get an object. And the default behavior of boto3 is actually when a request fails for a bunch of known reasons, so rate limit, unable to connect, a few other ones, it will sort of sleep for a bit and then retry again. And this kind of backs off as well. So, the next time it tries again, it will sleep for a bit longer and then longer and longer. So you might start off with a request that would normally take, 10 to 100 milliseconds, and suddenly it's 30 seconds long. And that's a big change. And the thing is, when it does this sleep, until it runs out of attempts, it never shows any errors. It never gives you an indication this is happening. So it's just meant to smooth over a lot of operational problems and make your code work nicely. But maybe in this case, it's actually working against us. So the theory we had was, we're almost eventually succeeding, but sometimes it take a really long time. So we think it might be because of all these retries and sleeps. So the next thing is we have this theory. Now we need to be sure. How can we be sure it's retrying? Like, is this actually what's happening? Are we just going down a complete rabbit hole? This is some other problem entirely. So, as I said, there's no indication directly from calling boto3 in the response that this is happening. So we're going, okay, what's the first thing we could do? We could turn on logging. So boto3 does a lot of logging if you turn it up to the debug level, and that can be really useful. Unfortunately, it's a lot of logging. This is actually a snippet of the logs you'll get at debug level when you do one request to boto3. It gives you a huge amount of depth. And obviously, as not an option in even anything more than a script. The actual content of this doesn't matter. Just the point is this loads, and it went shot off the end of the screen. And so it doesn't work even on a single machine. It's certainly not going to work in a big cluster of Fargate containers. We could generate potentially gigabytes or terabytes of these logs and then have to sift through them. And no one wants to do that. So the next thing we're going to go in, is there some kind of hook or some function or something we can call? And it turns out, yeah, boto3 does have something like events. They're a little bit buried in the docs, actually. One of us only found it by accident that this even existed. So we basically had to, start looking at this going, oh, this could be useful. And so, yeah, there's boto events, which are, you get your client, and you use this fairly buried call, like meta events register, to register a function that will get calls based on different patterns. And the pattern can basically be the event dot the service dot the function call. So you can wildcard these as well as star, although there's some limitations. I think you can only put the star at the end, so you can't wildcard the bit at the beginning, for example. So, you've got this hook. This looks promising. But as I was saying, the docs may be missing, but so let's see what this does. So this is just a small snippet of code where I'm using boto3. I'm getting the S3 client and EC2 client to talk to their APIs. I'm registering the event hooks, and I'm basically printing the event name. I just want to see what are the events you can get. So I run this, and I get this output, which actually shows there's quite a lot of events. Like every single request generates all these events, which is probably why the logging is so robust, because each one of those probably generates a whole bunch of logs as well. And eagle-eyed might even see some events that look like good candidates to research. But you'll see there's like before a request, during the request, after a request. So we're getting these events, and now the question is, what's in them? So the second bit you get is your function will get called with a whole bunch of different arguments depending on the event type. And so since I have no idea what they are, I'm going to basically use this keywords arg trick in Python where star star will capture it into a dictionary, and I'm just going to print it because I want to see what the heck is going on here. And again, I'm going to get a client, and I'm going to register this event for everything, and then I'm just going to see what's happening when I call it. And so here's one of the examples, request created. So here I'm showing both the dictionary you get and then how your hook would be called with that. So what kind of function signature you need to write to make this match, or rather to make it match and not fail because it can't pass the arguments in. And then here's another one, needs retry, which hopefully is still legible. Yeah, it is. And so this one's starting to look interesting. This is starting to kind of get interesting because you're seeing one part of this looks really interesting, which is the attempts and caught exceptions. These fields look really interesting. They might be something useful here. Now the problem is we have this, I've reverse engineered this. So we kind of have an event to watch. We think it's going to be something useful, but I've only been able to call it when I successfully call from my client, from my laptop, so I could get like one success and sort of that looks good. But what does failure look like? What's this going to look like in production when it goes wrong? Unfortunately, all these events aren't really documented, and they're all dynamically generated in boto3's code. So it's very hard to kind of unpack boto3 and reverse what these are going to look like. There's no actual explicit class or function that does this. It's all dynamically generated based on the responses. So we've got an event that looks like a good candidate, but now we need to know what it looks like for real. As you saw, your function gets called with different arguments. And I don't know at this point, does it get called with different arguments when things go wrong? Like if I write a function now based on what I'm seeing, will it fail in production because it's getting called with something different? So I need to figure out what this looks like for real, and I can't use the docs. So there's a few ways you can do this. You can trigger it for realsies in production, which can be an option, but can be very, very, very expensive. It would have been in this case, and very slow and tedious as well. I could start modifying the boto3 code. Or insert a debugger, but that may or may not be possible. And also you have the problem then, you have to kind of reverse mentally model the code in your head and figure out where to put stuff. I could start hacking the interpreter, putting debuggers in there. I could hack the OS, put more debuggers in there. So you kind of get different views of things and you get different levels of complexity. And this is where it depends a bit on the tools you have to hand and your experience, like you reach for different things. And in my case, I've been doing a lot of networking over the years, so I was going, you know what, I don't want to care what the code looks like. I want to make it think it's getting this problem on my laptop so I can see what it does. And so I'm going with the option of hacking the network. I'm going to basically try and take requests and modify them. So to talk about that, I need to explain a teeny bit about HTTP to make it relevant here. So all the requests to this AWS REST 3 are over HTTP. It's a very simple protocol, but the bits we care about are when you make the request, you send GET with a host header, and then you get a response. You usually get some status line, and then some content type fields, and then the payload. So the status line is the one of interest, because I mentioned before, when I mentioned before that I think AWS uses HTTP 429 for rate limit errors, I'm going to make a bunch of bets now. I'm going to make a bet that AWS uses these 429s for too many requests, because generally they're not crazy when they design their protocols, so they don't do something outside of the norm. I'm going to bet that boto3 looks at this response code, the first thing it looks at when it gets the response back. I'm going to bet that when it sees an error, it's going to ignore everything else. And so that makes my life easier, because I can modify this response, and then it's going to realistically trigger the error cases. This may not always be true, but in this particular case, I'm making a bet that it just looks at the header, sees the 429, and goes, oops, I'm going to trigger my rate limiting code. And what am I trying to do? So what I need to do at this point is I need to go from success, error-free requests, to broken requests. I need to actually simulate a broken response. And so that's where I get to the other part of the title of this talk, which is mitmproxy. So mitmproxy, or man-in-the-middle proxy as it's known, is a free and open source interactive HTTP proxy, or HTTPS in this case. It does HTTP, HTTPS, I think it does TCP as well now. And it's a bit like Chrome dev tools. If you ever do the inspector and you see the network traffic and you sort of right-click on a request and you can get all sorts of details, it's basically that, but in a generic way, so you can intercept stuff in any process. And so it's really useful. It's Chrome dev tools basically for any process you have on your machine. And how do you use it? Basically, you run mitmproxy or mitmweb. It will bring up either a terminal interface, which is the one I tend to use because I'm that kind of person, or mitmweb brings up a web interface that you can connect to and use. They're identical, basically. You set the proxy setting on the process you want to look at and get it to proxy its traffic through mitmproxy. So using one of the kind of standard settings to proxy HTTP, HTTPS. You run your program, and then you should be able to see all the traffic coming backwards and forwards in mitmproxy. So here's a really simple example where I'm going to use HTTPX to do a HTTP GET from HTTP bin, which is a handy little site that lets you just sort of fire a request in and it sort of responds back with information about the request you fired and lets you just sort of debug requests. So I'm going to run this. I'm going to run this by setting the HTTP proxy first. So you set this, the classic way you do this in most Python programs that do HTTP is you set this HTTP proxy variable or a HTTPS proxy variable in the environment, and then you run your code. Some of them will require you to edit settings, some will change depending how you use it, but that works about 99% of the time. And when you run mitmproxy, hopefully that's visible, oh yeah. So when you run it and you do the request, you get, basically you get a nice little console showing there's my request. I can click into it or press enter to go into it, and it shows a whole bunch of information. So here's showing the request I sent, so you can sort of see the user agent, you can see all the headers. Then I can also look at the response, and it kind of shows you the headers you get back. It even, if it spots that it's JSON or something it recognizes, it will format the code and everything for you. It's really nice. And then you can also look at sort of other properties that will show you what's the IP you connected to, what protocol was using, HTTP1, HTTP2, something else. Here's some timings. How long does it take to connect? How long does it take to get a byte back? How long does it take the response? So you get a lot of information, the same sort of Chrome dev tools, but now you can do this for any process. So that's super handy. So let's try this for S3 now and see what we get. So wrote a tiny bit of code, S3 get object from a particular bucket with a key. So I was getting a particular bit of code, data. And I'm going to set my variables, so HTTP and HTTPS proxy, so I do both. I'm going to run my code, and let's see what happens. Oh, that's not what I expected. That wasn't a great feeling when I saw this. So what's unfortunately happened here is I got a SSL certificate error, or a TLS error. What the heck is that? So what's happening here is transport layer security, as the name implies, is kind of doing its job. And it's not what I want it to be doing right now. So here's a quick example where I'm using curl as a tool to fetch fourtheorem.com. So this is kind of a typical HTTPS. This is a hand wave abstraction simplicity of the connection. But basically, you connect, it does this hello, and then you get a certificate back. Then the process, so curl in this case, will go to the OS or certificate, some kind of trust store where it has all the certificates. It'll go, is this legit? It goes, yep, that's who it claims to be. And then it continues on and does a request. So that's the normal thing. And that's what I kind of wanted to happen here. Unfortunately, when you introduce man-in-the-middle proxy as a man-in-the-middle, which is a thing TLS is explicitly designed to prevent happening, what happens is you make your request to man-in-the-middle proxy, which gives back its own fake certificate. It's not for theorems because it can't sign it because it doesn't have the key. Curl goes back to the trust store and goes, is this legit certificate from fourtheorem.com? And the trust store says no. And curl just stops at that point and gives you a big error. So that's actually working as designed, but not as we want right now. So luckily, mitmproxy does generate a bunch of certificates, a whole certificate authority kind of chain, and sticks it in a folder. So we can use this somehow. And so one thing, though, I'm going to point out, I'd be remiss, you could reconfigure your OS to use these, to trust these certificates, and then every process will be able to talk to mitmproxy. That'd be great. Unfortunately, if your machine is compromised, everything, all your traffic can be intercepted, so that's really bad. So don't do that, unless you really have to. Like if you're doing iOS mitmproxy, you kind of have to do it because there's no other real way to do this. But I wouldn't recommend it. Now, luckily, we don't have to do that. We can actually we can override these certs on a request by request basis. So we just do it when we need to. So what we do is we override it. So we say, okay, do this again. So we say hello, connects to mitmproxy. Mitmproxy gives back a certificate. It goes back to the trust store, which we've now injected in our own mitmproxy certs. It goes, yep, this is cool. And continue, and then you go on. Mitmproxy now makes a request to the other side, so fourtheorem.com. It does the same dance again, goes back to the store, verifies it's correct. And then, you get request is done, you get the response, and everything's great. So it's working. So the question is, how do you do this in boto3? And this actually was the hardest part of all this, because I could not figure this out for ages. And I actually did have to crack open the code and root through it. And eventually I found there's this environment variable you can set called AWS CA bundle. Funny enough, I found the docs afterwards once I knew what to search for. I could search in the docs going, oh, there they are. But basically you set this, and it'll change the behavior of boto3 to use this bundle. So when you need to override it temporarily, you can set this in an environment variable along with the HTTPS proxy, call your code, and fingers crossed, it works. So now I can see my S3 requests in mitmproxy. This is great. Let's have a look. What does an S3 request look like? It's a lot more stuff than you might think in there. There's all the authentication. There's like all the signing, authorization. There's even an attempts field, which I found really interesting. I hadn't actually noticed that until recently, so that may have been something to look at some point. And you get a response back with a bunch more fields. In this case, the file is hello, so there's only like 6 bytes of data in it. But you get a whole bunch of, you can actually see like, a little bit about the server-side encryption used and everything. So you get a bunch of interesting information back. And here we can see the Amazon certs. You can see that they've basically created a wildcard cert for all the S3 stuff, because I guess they don't issue like a cert per endpoint. So you get a whole bunch of information. You get timing information, the HTTP protocol used, HTTP 1.1 if anyone cares, not HTTP 2. So we've learned a lot at this point, and that's cool. But does that help us solve our problem? So one of the good things about mitmproxy is it's more than just a debugger. Sorry. You can edit requests. So here's an example of how you do it by hand, where you hit I to create an intercept, like when you're in the mitmproxy. You type in this match expression. It's basically match on this domain, so I want to match an S3. And you want to match in a server response, not the request. And you run the command, and then what will happen is it will do the request, get the response, and then stop. So then you can go into it, hit E to edit it, so you can edit the response, and then you change the response code to 429, and hit A to allow it to continue on its way, and then see what happens to your S3 code. So here's an example where I fire up my mitmproxy. I hit I to enter an intercept. It's kind of tucked away at the bottom corner there. You can see me entering the expression. Then you can sort of see it's set now, so it shows that it's set. I do the request, and you can see when it's intercepted, it's not green, it's sort of red. It's sort of showing it's a different color. And you can see here that it's even showing response intercepted. So you kind of see it's the same kind of UI, except now it's showing us intercepted, so it's holding it. So I can hit E to bring up this little menu, and then hit C in this case to edit the status code. And then down the corner, I type in 429, and then you'll see that it's been edited. So it's now saying 429, OK, funny enough. I didn't bother editing the message, so it's 429, OK, which just ignore that. And then I hit A to allow it to continue on its way, and it returns back the 429. And you can see here, yep, it's a 429. So it's as if the server responded with a 429 at this point. Same payload. I've only edited the status code. And you can see here, in this example, I'm actually using the AWS CLI. And interestingly, it doesn't do retries. It just simply failed straight away. So there you go. So I did AWS S3 LS, failed straight away. So it works. That's the important thing. Now, all that typing is fun in mitmproxy, but I'm lazy. So what I wrote instead is, you can do scripting hooks, add-ons they call them, in mitmproxy, where you can just write a bit of Python code. Here you can see I've added a filter, which is the same query. Then I intercept if it matches, and then I edit the response code. And I also change the reason, because it's kind of weird seeing 429 OK. The reason doesn't actually matter, but it just annoys me no end. And so to run it, you go mitmproxy -s, my script. And you'll see here that in the bottom left, there's a scripts 1, so showing that you've got one script running. And so I run my AWS S3 LS, and without me doing anything, it's intercepted it, rewritten it as 429, and done what I want. And you can see here that it's definitely done it. So, fun fact, S3 is so old, it uses XML in its responses. So you have to write an XML parser if you want to deal with S3 at the low level, if you're not using the SDK. So the great thing is now I can do lots of requests and testing without having to type in IA, edit the thing every single time. So that's good. Suddenly this gets a lot more fun. So now I can intercept this. Let's actually look at what the heck we get back. So that's just the whole point of this. So I write a tiny bit of code. I'm going to get the event name, the number of attempts, and the status code of the response. I actually got printed more stuff, but it's too big to fit on screen, so I just simply cut it back down again. But essentially, I just want to see what the heck this looks like. So you can see it running in mitmproxy. You can see it retrying. So you can see it should be 5 requests there. There's like the original one, and then 4 attempts to retry, and eventually it fails. it gives up. And here's the output. You can see attempt 1, 2, 3, 4, 5. Now, this is actually something I learned while doing this. I had mentally assumed they start on 0. And so the first number would be the first retry. No, they actually start on 1. So even though your first request is not retry, the retry count is 1, which kind of messed me up when I was thinking about that for a while. So I keep getting if I say it's 4 retries or 5 retries, it's because I keep getting myself confused over this. But now you can see it's retried, and so I have these numbers now. So this is the important learning, was actually from all this was that, oh yeah, it starts at 1, which means that what I have to do, I ignore everything at 1. I only start checking for retries at 2. So now I can finally generate metrics. Woo. So I can use these to debug what's going on. See, in production. And so you can see here it's using a simple statsd format where basically I write a hook. I check the number of attempts. If it's greater than 1, I call my hook and increment this metric with the name of the event. And then otherwise, I just don't do anything. And I register the hook and run my code. And it's still running against mitmproxy. This is all still running on my laptop. I don't have to do anything in production. And yeah, it does the job. It intercepts, increments, ignores the successful first attempt, or air quote successful first attempt. So I don't get spurious counts. And so I could deploy this production and see how bad things really are. And so, yep, it was pretty bad. This graph, unfortunately, Log Insights has helpfully chosen gray as a background, but that peak is 250,000 retry attempts in a 1-minute window. That's quite a lot. And so we were going, yeah, that mightn't be good. So yeah, that's probably what's happening here. We should fix that. So yeah, each horizontal tick there is a minute. And it's like, it was basically millions of retries over 20, 30 minutes. And yeah, that adds up. If each one of those even takes a second, it starts adding up. And especially as all these jobs, some of them might depend on each other. So some are waiting on some to finish. So suddenly this just blew out all the times. And so finally, after all that, we have some kind of success. We basically, what we did is we talked to AWS and they upped some limits for us, but that's another story. We finally could figure out what was actually causing the problem, which is great. But yeah, so this is a whole journey where we had to we're starting with someone saying this is taking a long time. We kind of had a theory about what was happening, but we needed to prove it, and we couldn't use logging, so we used events to figure it out. And then we wanted to somehow modify the responses, and then we could use mitmproxy to intercept that, and then we could change the responses so finally we could see the shape of the response when there's an error, and then finally we can emit metrics, graph them, figure out the problem, prove it is what our theory is, and then fix it, which is great. So what did I cover here? I mean, basically, how do request retries behave? The fact that there even is request retries is sometimes a surprise to people in boto3. Knowing that can be very useful. AWS APIs have limits. They just have to do it. Unfortunately, they're not infinite. mitmproxy is a lovely tool. I really like it. I always like to break it out at every opportunity, which is why I approach this problem this way. boto3 has an event system, which actually I think for a lot of people was a big surprise who've been using boto3 for a long time. And yeah, nothing is ever simple. Like you run into little problems with these kind of debugging things, but it can be worth persisting. And with that, I'm going to put up a link to the slides again. And that is me done.
Have you considered a caching system or a worker thread that would delegate the requests to, so that you don't run the request to the same object every single time for each of the requesters?
So the question is, have we considered like a caching system so that we're not all kind of hitting the same objects all the time? The answer is yes. One of the properties of this system was we wanted to make it embarrassing parallel so that no job depended on each other's state. And we did look into a caching system, but the hit rate was terrible because it was almost randomly distributed. Like we're still looking at a way to do this because it is definitely a problem. And as it gets bigger and bigger, we're going to hit some limit we just can't get around. But for now, we prefer the simplicity and just being able to ask AWS to up a limit somewhere for us.
This might be more of a question for AWS, but are you surprised or interested in how there doesn't seem to be exponential backoff from the retries? So
the exponential backoff is a retry with jitter algorithm, which is very commonly used in these high production, to make reliable systems where you might get a transient error. It might only last a second or two, and you don't want all your stuff to fall over because it gets cascading failures. So you you add this retry mechanism to kind of paper over it, basically, so your stuff keeps going. I mean, honestly, most of the time you do want this. It actually covers a lot of errors, like just, little transient errors. But the back off is to stop it like repeatedly hammering, which can make a problem worse. Like a system is under stress, and suddenly every client starts retrying, and all the clients start backing up and retrying. They start hammering like crazy. And then the random jitter it introduces in the sleep is to make sure they all don't synchronize. You can get this funny problem where all the retries start synchronizing, so they introduce this as well. So it definitely it's a good thing most of the time. It's just, in this case, it was implicit, so we couldn't see it was happening, and so we had to like figure out, is this actually what was happening? So we had to do some poking around to figure it out. So that's when it's not great, when you don't want that. But to be fair, we couldn't just turn it off, because there were cases where you get just a few seconds of transient failure, and then you don't want all your jobs failing because of that. So it is useful.
Sorry.
Cool.
Thank you so much, Michael.
Thank you.